Welcome to episode 3 of Science with Jake. Today we're going to talk about the action potential. Let's just start with a pure definition. So an action potential is a rapid change in the electrical potential of the membrane of a cell, specifically a neuron that we're looking at here, that allows for the transmission of an electrical signal. Just think of it as a change in charge. You have something that's negatively charged, really quickly changing to positively charged. And this all has to do with ions, which are charged particles. This does get a little more complex than sort of the layman's conversation, but keep following along and it'll make sense, don't worry. Before we can talk about the real action potential, we have to understand what resting membrane potential is. I am putting it on the screen because it is that important. Let's start by zooming into the plasma membrane of a neuron. You know, I've been saying cue the overlay, but it's technically not an overlay because it's not a video over a video. This is more like the green screen. So 3, 2, 1, cue the green screen. We have made it to the membrane of a neuron. Let's take a look at this picture and talk about what we're looking at. On the top side of the diagram, you'll see the outside of the membrane, and then you see the membrane itself, and then underneath that is going to be the inside of the cell. Notice that we have all these positive charges on the outside, negative charges on the inside, indicated by the positive and negative signs. And then we have these protein channels, 1, 2, 3 labeled right there. And there's actually another important one that I don't have labeled here. I'll show you that diagram in a second. But for right now, let's just talk about these. So you'll notice this first channel here, that is called a potassium ion leakage channel. Then we have these two channels that I'm not really going to talk about right now. We'll save it for the next video, but these are your voltage gated sodium ion channels and voltage gated potassium ion channels. Voltage gated just means that it requires a change in charge to be activated, but we will talk about that later. So don't really worry about that for now. Most important thing in this picture right here is going to be to see the charge that exists at resting membrane potential. That is negative 65, also sometimes you see around negative 70 millivolts. What that means is that the inside of the cell is relatively more negatively charged than the outside of the cell. Now you might be wondering, why does this happen? Well, I'm going to tell you. Notice here you also have this thing that says pK greater than pNa. What that means is that the permeability of the membrane to potassium ions is greater than the permeability of the membrane to sodium ions. In a general animal cell, the concentration of potassium ions is high on the inside of the membrane, and the concentration of sodium ions is generally high on the outside of the membrane. But we have these channels, these leakage channels, and that's the diagram that I haven't shown you right now. And you know what, for now, I'm not going to show it because I can just pretend that that potassium ion leakage channel is just a sodium ion leakage channel, and then it's pointing downwards, meaning that the sodium is leaking from the outside in. These leakage channels exist, and even though leakage is happening in both directions, leakage of potassium outward is far greater than leakage of sodium in. There's also one very important membrane protein that is involved in maintaining this difference in concentration between potassium ions and sodium ions, called the sodium-potassium pump. You've got these potassium and sodium leakage channels happening over here. Over here, though, every time this pump activates, it is moving 3 sodium ions out of the cell and 2 potassium ions into the cell. So, by the action of these channels and the movement of ions through them, we have a higher concentration of sodium outside the cell than the concentration of potassium inside. Even though both are high, there is more sodium outside than potassium inside, and that leads the inside of the cell to be more negatively charged. Finally, I will show you this diagram, which is also very important. It shows you the action potential, which we'll talk about that spike. But over on the flat line right there, which my finger can't reach, that flat line at negative 65, that is your resting membrane potential before the action potential begins. Okay, I know that was a lot of information, but trust me, this was really important. You need to know the resting membrane potential and the concept of these channels that move ions in order to understand the action potential. In the next video, we're going to talk about those voltage-gated channels, which were closed during resting phase, and talk about what happens when they open.